We had a look at how a computer operates internally with the so-called machine code, and we had a look at how humans make that a bit easier to digest by using assembly code instead, which is very, very close to machine code still, but already a lot more convenient to work with. We also had to look at the full instruction set this specific CPU uses, so I feel like we are well equipped indeed, for today's task, where we will try to actually program something, to have a look at how assembly helps us get a better feeling for it, and just to get a feel for how we program in the first place. Our goal for today will be to write a simple program that takes two input numbers and generates one output number from it. Let's start with the very, very basic addition that we've already done in the past. So let's first define some numbers. We're gonna have an A, which we're gonna start with, let's say 10, and we have a B with 5, it's B, and we want to generate an C, which is our output, which, well, we're just gonna keep that 0 for now. And to add these two, we can just write the accumulator, just put A in there, then we're gonna add B, and then write the result into C. And that is already a functioning program we could operate on. I could go through these steps individually, but I feel like we're past that, so instead, for the rest of the day, I'll just work by instructions in total. Makes everything a bit faster. So we go back, forward instruction to the next one. We've now added the value of 10 from A into the accumulator, and complete that next instruction, the add. Now we have 15 in the accumulator, and then the last instruction, read from accumulator, has put the 15 into the memory. And of course the 5 would now get interpreted as an operation, and that causes all kinds of fun stuff to happen. Going back to our start condition, we have a simple program that takes these two numbers and adds them and puts them in C. I want to do something more complex now. Instead of adding these two numbers, I want to multiply them. Multiplication doesn't exist in this computer. There is no multiplication that I can just use. Doesn't work. So we are now faced with the basics of programming. We have a set of tools, the instruction set given to this or by this computer, and we're given a goal: add A and B, or multiply A and B and put them in C. And all the rest is up to us as the programmers. So we're gonna start by making a plan for how we're gonna do this magic trick, which it almost is. Let's go to please just work. Seems good. Seems good. All right. Multiplication. So we've tried That's not the pen. There's the pen, there's the pen. 10 plus 5, which was 15. That was correct. But now we want to try 10 times 5. Let's pretend we don't know what the result is. We need a computer for that. It's very, very complicated operation. Well, at least when I was in school, the way it was explained to me in the very, very beginning, like the very concept of multiplication, we would look at this and think, oh, 10 times 5 means 5 plus 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 5. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 fives added together. And that's 50. So we've done our calculation by just doing multiple additions. It's a bit tedious, but that's for the computer to do, not for us, so tedious doesn't really matter anymore. And more importantly, addition is something we can do. But we know how to make an addition happen in the CPU. And with this little strategy, we also know how to do multiplication. We just have to take any multiplication as just a series of additions. Alright, let's start with that. We make additions. A series of additions. Well, we already have the addition here. That works out. Let's set a goalpost in the end. Write our O. See, the end result should, when the program is finished, be displayed in the input-output. That's our signal that the program is done. And that also means we can easily spot the end result without checking the memory directly. Now for the actual program, addition makes sense. We're gonna need some addition happening. The write AC to C itself, let's ignore that for now. So we write B to the accumulator. That's our first 5. And then we add 1 5. And then we add another 5, and then one, another one, another one, another one, another one, and so on. Well, I could now just make 10 additions in here, or well, 9 additions, and this one right to accumulator. But that's not exactly the way to go, right? Since this only works if that's exactly the number we have in A. If A is anything else, like maybe just a 1, well, this is where we should stop. There should be no addition. Well, we could make things a bit easier by just making this an add as well, since at the beginning the ALU is 0 anyway, and adding B to 0 will just be B. So there's no difference if the first command is a write to accumulator or an add. And this way we have the exact number of additions we require with A, so that would work. But yeah, we have the issue of this number determines how many additions we have to make. So we can't just write that number of additions in our code and have it run. That's only going to work for very specific input numbers. We need some way to repeatedly make this add operation run without it being written several times in our code. And to do that, we can use the jump operation. We know that one. Let's say this is the start of our program, and this will then jump back to the start. So we add B to accumulator, and then we jump back to the start, which is this. So we add b to the accumulator, then jump back to the start, which is this, and we add b to the accumulator, and repeat, add b, jump back up, add b, jump back up, for all eternity. Sure, we will hit an overflow at some point, but that's not gonna stop anything from running, so we'll just keep adding forever and ever and ever. At the very least, we're not locked into a very specific number of additions anymore, so I think this is progress. We do, however, need some way to limit how many times we jump back. We need some way to stop repeating this addition once we hit the number of adds we need. How do we do that? One thought, we could keep a counter running that helps us identify how many times we've made that addition already. That might be helpful. So let's do that. We have another variable, let's say counter. And this will be the address we use to store the number of times we've made that addition happen already. So every time we've made an add, we're gonna need to increase that counter by 1. Well, how do we increase counter by 1? Well, we write counter to the accumulator. And then we're gonna add 1. But that doesn't work directly. Ooh. My screen's gone. There we go. Add expects us to provide an address, and if I just write a 1, it will expect address 1, which is right now this reference here. If I want to add exactly 1, I need to have an address where we store a 1. And I could do that down here, call it 1. Like that. But the rules don't prohibit us from using numbers as names, so I'm gonna do that. Makes it a bit easier to read. And it gives us a nice little convention for our names. Nothing that's determined by how the computer expects us to write things, that's just some way we decide to write things out. If it's a combination of letters, if it's a word, then it's a name for some part of the memory that's gonna change. And if it's just a number, then it's a reference to a memory address with exactly that number. And it's not gonna change. So whenever we need a 1, we can just use this reference and we know it's gonna be 1 exactly. The same way we could make 5 anywhere in there and have a memory address with a 5 named 5. This would be a convention, a coding convention that makes our life a bit easier, as long as everybody agrees to follow that convention, of course. That's the downside. It's not enforced, it's not a requirement, it's just meant to make working in a team easier. If someone else sees my code and they operate on these same assumptions, using these same conventions, this will make sense immediately, without looking up what this reference actually means. And then we read the accumulator back into counter, and we've increased counter by 1. But because we've written to the accumulator, we've overwritten the result from the addition before. So we have to make sure that the result from here, actually let's put it up there, and you couldn't see what I clicked. So we've written to the accumulator and overwritten what was inside the accumulator, which was the result of the addition. So before we make the addition happen, we're gonna load the previous value we remembered. Then we're gonna add b to it, and then we write that into C. So it's not like before with the addition, where we only wrote to C once the entire thing was finished. We now load stuff into the accumulator, modify it, and then store it back into memory to be stored for later, to be safe. Because those memory addresses, or addresses, plural, can be specified to have very specific use. We can't say C is only used for this one thing and no one else is touching it, because that's memory cells. There are enough around for everybody. But the accumulator is this one specific memory cell that's used by everybody, by necessity. They can't use a different cell and keep the old value in there. They all have to share this one resource. So they have to make sure that they clean up themselves. They load the stuff they need before they can use the accumulator, then make their modifications happening inside, and then read the results back for themselves for the next time we execute this. So we have a bit more code now, but well, let's also change this name to up there. But now we have the addition happening in here, which will constantly increase C by adding B to it. And after that we have this counter getting increased by 1. Let's just look at the program happening to make sure that it's working out correctly. Have a look at these last memory cells here. 18 is our C, 19 is our counter, 20 is 1. You can see 18, our C is constantly getting increased by 5 and our counter increased by 1. 20 to 4, 25 to 5, 30 to 6. So that part works. We now have the system that's doing the addition repeatedly and a system that keeps track of how far we've progressed with the counter. Now we need some way to react to the counter being equal to our A. Let's go back to the 10 in our example. We have to compare A and our counter. And once they are the same value, we want to stop repeating. Well, let's start with the simple problem. Stopping the repetition when we reach a certain goal. In other words, we want to change the behavior of the program depending on a certain condition. And for that we have conditional jump operations. We have jump a flag, which reacts to the accumulator flag being set or not. And we have jump a 0, which reacts to the accumulator value being exactly 0, or well, not being 0, depending on how you look at it. So if we use one of those conditional jump operations, we can simply jump past this jump and let's like that, jump straight to end. So we could do something like jump a flag, for example, end, and if the flag is ever set, then this will jump straight to the end here and program is done. And if it's not set, we would hit this jump operation and go back to the start and make another repetition. Of course, that would also work with jump of 0. Same result. So we could make a couple of repetitions until at some point the condition, either the flag or the accumulator value, determines we now take this alternative jump beforehand and end the program. Alright, let's keep that in the back of our minds. I'm just gonna leave that there. How do we now compare counter and A? Our instruction set doesn't have anything for comparisons. So what can we do? What operations are available to us that would allow us to compare two numbers? The answer is surprisingly simple. We have a subtraction, and a subtraction can be used for comparisons. If you think about it this way, if you subtract a number from another number, you just determine the difference between these two numbers. And if that difference is 0, then the two numbers must be equal. Actually, we can do even more than that. If we were to just take the current value of our A in the accumulator, and then we subtract the counter, what's the end result going to look like? Well, in the beginning, A is 10 and counter is 0, so the end result will be 10. Then one iteration later, we subtract 1 from 10, so the end result will be 9, and 8, 7, 6, and so on and so forth, until we at some point hit counter being equal to 10, at which point 10 minus 10 is 0. So at that point, the accumulator value will be exactly 0, so this jump operation will trigger. We'll jump to the end. We could also go a step further, and instead waiting for the counter to being equal, we could wait for it to be bigger. Because once counter is bigger than A, well, once we subtract the counter from A, we'll hit a negative value. Negative values are something this computer doesn't understand. We've talked about that. Instead, we'll hit an underflow, which means the value will be a pretty big number again, most likely. But more importantly, the underflow will set this flag. So we could, instead of a jump of 0, then use a jump of flag, and that would trigger once counter is bigger than A. So just by subtracting two numbers, we can either check for the flag to be set to know if the number we subtracted from the first is bigger. We can check for the accumulator being exactly 0 to see if they are both equal. And if neither of those happened, if the set flag wasn't set and the value is not 0, then the second number was smaller. But for us, it all just means this will tell us that the counter has reached the number determined by A. Let's just try running this, shall we? Actually, let's make the number smaller so we don't have to do as many repetitions. But just gonna operate on this, just see what it's gonna end up as. Oh, there it was. We reached the end of the program. Write IO is triggered with 15, which is indeed 3 times 5. So we successfully wrote a program now that can multiply 3 and 5 and writes it to C. That's good. Let's try a different number. Because this program isn't perfect. It can make mistakes. Let's say A is 0. 0 times 5, well, the output should be 0. Well, that doesn't look like the program made the correct choice, does it? Because A was 0 to begin with, we subtracted 1 from 0 and got negative value, which did set the flag, but we don't check for the flag, we check for this being 0. But instead we hit the underflow, the value was greater than 0 in the accumulator, and so our jump of 0 never triggered, and we skipped over the number. That's an issue. Well, we can just account for that by making a quick check at the start. Let's just write A to the accumulator and then jump of 0, and if the value was 0 to begin with, we just jump straight to the end, and that's that. So output is 0, program is fixed. And actually, to save some time, we can do the same with b. We check if b is 0, because repeatedly adding 0 doesn't really do us much good. So this program works just fine. Let's change this up to 10 times 0. This time is 10 times 0, load the program. Output is 0, which is correct. All right. We have now a program that will multiply two numbers and give us a correct output. The product of the two factors. Great. But this program does take quite a bit of memory. Like, it's just a simple multiplication. We just want to multiply two numbers, and we use a lot of code to determine the behavior and have some additional requirements for extra space just to store temporary variables and these constants here. Can we optimize this program somehow? Yes, we can. I mean, of course we can. Dumb question. But what options do we have? Well, for starters, why do we bother with the counter? See, the only reason we have the counter is so that at some point we can compare it to our A, and if the result is 0, we'll stop. Now let's imagine the counter not counting up, but instead counting down. If we subtract 1 from our counter, subtract 1 from our counter, and the counter starting at, for example, 10, then we could skip the comparison oh, wait, not like that. There. We subtract 1 from the counter, and once it's 0, we'll know it's done. We've hit 10 repetitions. Which would mean we have to write the value to the counter. So after checking for 0 up here, we still have the accumulator filled with A. We could just do this and put it in counter. So counter will always be equal to A after the program runs this. But that also means we could just skip the counter altogether. We don't need it, because we already have A, and we don't really use A anymore after this. So why not do just A instead of a counter? So now we check both for null, or for 0, and if it's either of them is 0, we end the program. But otherwise, we start this repeating code that will first add B to C. Actually, let's rename this. Product. And product. That's better. We'll add B to the current state of the product, and then we'll subtract 1 from A. And if we reach 0, we'll just stop. And if we didn't reach 0, well, we jump back to the addition. This already saved us quite a bit of space. For one, we didn't have to add the extra code for counting down the counter and comparison. We're just counting down A directly, and we still make a comparison, but also on A directly. And we didn't need to store counter anywhere, so we save some space. Good. We can improve this further. Down here, we'll jump to the end when A is 0. Up here, we jump to the end if A is 0. What we can do is we can move the subtraction from A further up before the addition. So first we subtract, then we add. Neither of these blocks really affects the other, except for this jump. But they don't interfere with each other's values, so the order doesn't matter in that sense. But now, because the jump of 0 is up here, we can move this check over there. And now we have the same as up here, and so we can just drop that as well. So to start the program, we check if B is 0, just as a shortcut. If it is, we just jump straight to the end. But if not, we'll load A, compare if it's 0. If not, we subtract 1 and store that as an A, and we make an addition happen. Now, since we changed the order of things, we have to move the address further up. The loop repetition starts now up here. So we always have, first we check if it's 0, then we subtract 1, then we make an addition, and then we start back up, check if it's 0. Before we made the addition first, then subtracted 1, and then checked for 0. We just changed the order, and that alone saved us some additional operations and some memory space, which, well, every operation, every instruction takes some space away. So now we have a pretty decent working program for multiplication. It's not as nice as just having add or multiplication then mul, but it does its job, and it's doing so in relatively little space. That's fine, that's doable. The only issue we have with this now is the time it takes to process and multiplication. Like, let's go for the extreme example. We have 10 times 5, so 5 plus 5 plus 5 plus 5 plus 5 plus blah 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 blah. 10 additions. We'll just run through it. Actually, let's make a little change. I'm gonna add a 100 in here, which is an invalid value for an operation, so the CPU will just stop. So I don't have to worry about halting at the correct time. Just leave it running. Yep, there we go. It stopped right after it outputted the end result. So it took some time, and more importantly, it took quite a lot of instructions. If we assume that, in this CPU at least, processing an instruction will always take the same amount of time, if these 4 steps we have are always aligned, synchronized with a very specific clock, so every step of every operation takes the same amount of time, meaning the operations themselves take the same amount of time. Even if they skip a step, it just means nothing happens in there, but the clock will still cycle through that step. The number of instructions we use for our program is equal to the time it takes the entire computer to calculate something. So let's look at the instruction count. 85. It took us 85 instructions to calculate 10 times 5. Well, let me just note that down somewhere. Or 10 times 5 it was 85 instructions. Well, technically it was less than that, right? Operation 84 was already the output, but let's just count that. Let's make everything easy and just say we take the instruction count when we hit this stop. Let's use a smaller number. Let's use... well, let's for comparison just use 9. Just one less. Note the program. Let it run to completion. And we're at 77. So 9 times 5 is 77. And let's take a smaller one now, 4. $37. So quite a bit faster, which makes sense. Let's go down for 1. Only 13. And to you that should make absolutely sense, since all we do here is repeatedly add two numbers, and the number of times we repeat the addition is directly dependent on this value. The bigger A, the longer it will take to generate the output. So instead of making 10 times A, we could write a bit of extra code to flip A and B so that we have 5 times 10 instead. That would speed things up, definitely. Though of course that means we have to write additional code that compares the two and then flips the two. If there's a big difference between the two, that will make sense, that will help. If they are equal or nearly equal, then the difference will be not so great, and the additional code we use for swapping A and B is offsetting everything we gain by switching them. So there isn't too much we can gain anymore here. We can make small improvements still, potentially large improvements in extreme cases, but the algorithm itself is somewhat flawed. Repeatedly adding two numbers is slow. There's a reason we don't do that usually if you just multiply two numbers in your head or on paper. You've learned a faster way in school. At least I did. I'm hoping you did too. For that, let's get back to the drawing board. Let's come up with a new way to multiply. Just waiting for the technology to catch up. It should catch up, it should be here. There it is. So this would be the primitive way to do it. This is how multiplication was explained to me in the beginning. Not how we are supposed to do it, just the very beginning to see what is it in fact, what actually is multiplication. Of course, how we then actually learn to do that is by doing something like this. If I take 10 times 5, well, I'm going through these numbers now digit by digit. I'm starting with the first digit, this one, the 5 over here, and now I'm looking at the first digit over here, which is 0. And then I'm multiplying just these two digits, 5 and 0. And to multiply these single digits, we memorized a multiplication table. So we know the result of each of these possible combinations. There are 10 digits in total. So there are 10 combinations possible here and 10 over here. So 10 times 10, 100 different outcomes possible. And we just memorize those. We don't calculate that anymore. We could, in theory, still do that by hand with this method up here, but we have it memorized usually. And that's just the number we use now. 5 times 0 is 0. So we put on a 0. And then we take the next digit in here. And this is a 1. And 1 and 5 is 5. So we put down a 5. But because we're using the second digit over here, we have to move this over by 1. Instead of putting that in the first position, like with the 0, we have put it in the second position, like the 1 is. And we just fill in the gap with a 0. And then once we've done that, this digit is done, and we can repeat the whole step for the next digit. There is none, so we are done with this step, and we just add the numbers together. 0 and 0 is 0, 5 is 5, so the end result is 50. Going a bit more complex, let's make a bigger number. Let's say we have 137 times... what's a good number? 21. Right, so a couple of more digits. We have a 1 in here. That's the first one we look at. And a 7 over here, so that's a 7. Then second position, 3 and 1, it's a 3. We move it over by 1 and fill in the gap with a 0. And 1 and 1 is a 1, which is also 1, but this time it's the third position, so we have to move it twice. And fill in 2 gaps now with the 0. That means this digit is done. We move on to the next one. Now 2 and 7. That's 14. So we have to enter 14. But this is the second position in this number. So we already have to move by 1. We have to start by moving 1 first. And then we use 14. And then this digit, 2 times 3 is 6. We have to move it over once for here, with this number on the left, second digit, and because it's the second digit here, also 1. So we have to move it by 2 positions in total, meaning filling in 2 gaps, and then 6. And then the last one is 2 times 1 is 2. Third position, second position, that means we have to fill in 3 spaces, because that's how far we moved it over, and that's 2. And with that, we have this digit done as well. All the digits are multiplied. We can add, and that's 7, that's also 7, that's 8, and that's 2. And that's the end result. This is how I learned to multiply in school. Or I'm not quite sure how we explained this shifting over. We had some fancy little rule that's easier to memorize for elementary school children, but yeah, that's basically it. Now let's have the last example. Let's say we have... let's make a big number, 1010. And we multiply it by 101. I swear I can, like that, make a straight line. So we start 1, 1, or 1, 0, which is 0. And then we go for 1, 1, which is a 1. 1 times 1 is 1. We shift it over by 1, so it's that. And then we go for 1 times 0, which is 0, but shift it over by 2 now. And then 1 times 1 is 1, shift it over by... wait. 4, yeah. like that. And then we go for the second digit over here. This one is done. Which is going to be first a 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then last one is this one over here, multiplied by everything. And that's... Oh, wait, we have to do this. And the last one always start with 2 digits of ready. 1 and 0, 0, 0. 0, 0, and 0, 0, 0, 0, 0, 1. Like that. And then we can add them all up together. That's just 0, that's 1, that's 0, that's 2, that's 0, and that's 1. So 1010 times 101 is 102,010. Now this is a bit ridiculous, because obviously we could simplify things here a bit. We can take advantage of these numbers. Since all I'm doing is just multiplying ones and zeros, well, if there's a 0, the end result is 0, doesn't matter what the rest is. And if there's 1, it's just the other digit, no matter what it is. So if I multiply by 1 over here, I don't really have to check every single digit by itself, because it's already really clear which digits are going to be used or not, because every single digit multiplied by 1 is just the same digit again. So instead of writing that out as individual rows, I can just simplify it and see this is a 1, so I'm just going to take the original number. 0, 1, 0, 1. Okay, first digit done. Then second digit, it's a 0. Well, that 0 times anything will be 0, so I can just ignore it completely and not add anything. Done. And the last one is another 1. Well, just same as the first. It's just the original number. Of course, now I have to add a shift for it's the third digit in this number, so 2 zeros, and then the original number. 0, 1, 0, 1. And those added together still result in 102,010. But it's a bit shorter. This is more like what you would do. Now, the cool part is that this principle with the ones and zeros does not rely on the base of that number system. So everything right now, everything you see here is base 10. This is 1010, 137. Those are all base 10 numbers. But this on the right, this could also be base 3. This could be ternary. This could be base 8. This could be base 2. As long as it has at least 2 different digits, like base 2, any base system could be used for this and the roots would be exactly the same. At least this part up here would always look the same. Down here, that would need at least ternary, base 3, but this part up here stays the same with base 2. If it was binary, then instead of a 2 down here, we would have a 0 and a 1 carry over, and then a 1 here. So that would be the only difference. Just the addition will look a bit different. But why am I showing this? Well, the computer itself internally uses just binary. So it is only ones and zeros. And as long as it's just ones and zeros, we don't really have to worry about multiplying anything. We don't have to memorize any multiplication tables or try to iteratively work out the individual multiplication results for the digits. We just know it's a 1, then just take the original number. If it's a 0, just do nothing. No multiplication needed. We just take the number. At most, we shift it over a bit to the side and fill in the gaps with zeros, but that's it. That's all we do. If it's a 1, take the number. If it's a 0, do nothing. If you take the number, just make sure you shift it over first a couple of times, but then just add the numbers together. We know how to add, and you have an end result. This is something we can do in our CPU. We can recreate this exact method. Let's have a look at the CPU. Let's say we keep these 3 around and the output, right? Let's reset everything else. We still want to end with an output of the product. Let's keep also the name, it's the end. That's gonna be useful, certainly. And we have, of course, the 2 inputs, A and B, and the product output. And I'm gonna leave the 100 in as a stopgap to make sure we stop at some point. How do we approach this problem now? First, let's talk about figuring out if a specific bit in our number is a 1 or a 0. There's a way we can check that. Remember last time I showed you these 2 operations, bit shift right and bit shift left. Bit shift will literally take the original number and move it over to the left or the right, depending if it's bit shift left or right. And the gap that's appearing will be filled up with a 0, not unlike what we did with our shifting numbers on the multiplication just now. And whenever we shift out a digit in the number, in the binary representation of the number, the ALU flag will be set based on that bit that we shifted out. If the flag is set, it means the bit was a 1. If the flag is not set, it meant the bit that was moved out was a 0. So by using bit shift and then using a conditional jump a flag specifically, we can choose 2 different parts of the code that execute it depending on whether or not a specific bit inside the number was set or not. That's the simple explanation. So with that, we have a way to test the specific individual bits inside a number. In the multiplication, we always looked at the rightmost bit first, and then the second position, third position, fourth position, and so on. So by bit shifting right, we're gonna shift out the rightmost bit. So the number was a 10 like in our example. We're gonna shift this over by 1 to the right, meaning we're gonna lose the 1 and gain a 0 in front. So the flag would be set. And then with bit shift again, we would end up with 001. And 0 was dropped out, meaning the flag was not set. And doing another bit shift, we would just end up with 000 and the flag was set. So if we continuously bit shift to the right, we can look at every single digit or every single bit in our number from right to left. And let's use A for that, since A was the number that determined things beforehand as well. A is the one now that we're gonna shift over to the right. So right accumulator, A, we shift to the right, and then jump a flag. We're gonna jump if the bit we moved out was a 1. What do we do if that bit was set? Well, in our multiplication, we needed to add the other number, so for us that is B, to our sum that is the end result. Now for manual multiplication, we first collect all the different outcomes and then sum them all up in one go. In the computer, that's easier to just make the sum step by step. Once you have two numbers, sum them together. Once you get the third number, you add that to the previous result. So what we would want to do is we take the previous result, right accumulator, product, and then we add a new value to that and store that back into product. So if the flag was set, we want to add something. If the flag was not set, we don't want to add something. Well, how do we do that now? Well, first of all, jump your flag needs some target. Let's make a simple target with a knob. That's a harmless little operation. We can just use it as temporary stopgap to help us identify a position where we can do something. No, not skip add. Let's go after add. This is after add, and something we could do like add, like that. If the flag is set, we jump down to after add, down here. And that means we skip the add. If the flag was not set, we're going to execute this first and then end up here. Which is of course exactly the opposite of what we want. We want to perform this addition when the flag was set and skip this addition if the flag was not set. So we need this conditional jump here to behave exactly opposite to how it's supposed to operate. We can't do that directly with the instruction as it is. There's a workaround though. We can use the tools given to us by making another jump, and this jump will be moving to after add. And if the flag was set and this jump triggers, we're just gonna skip the after add and jump to add. Let's move this down maybe a bit. If the flag is set, we will execute this, which is the addition. If the flag was not set, we will go to this jump, which will skip the addition. We could do the same with a jump if 0. Also another conditional jump that can be inverted by just combining it with another add. It's a bit more annoying to handle, because now you have two different addresses you have to worry about, but this way you can invert any conditional jump. Instead of jumping if the flag is set, we effectively jump if the flag is not set, and for 0, we can now jump if the accumulator is not 0, instead of the usual only jump if it is 0. Alright, so we shift to the right, we check if the bit was set or not, and based on that we make the addition. That's progress, alright? We need to repeat this a couple of times though. So we're gonna need definitely another jump. How often do we need to repeat this? Oh. Let's just mark this as start so we have something to jump to. the numbers in this computer are always defined as 8-bit. They always have exactly 8-bit in total. Every time we shift over to the right or the left, we'll drop 1 digit from the original number and just fill in the gap with a 0. That means at most it will take us 8 shifts to completely clear out the original number. After at most 8 shifts, every single digit in there will be replaced by a 0. So we could assume that we couldn't just repeat this 8 times, and that would work, but we could be a bit more efficient about that. Because repeating 8 times means we need another counter to count how many times we've already made the shift, which is extra work. You've seen the counter earlier. And also, there's a shortcut we can take. 101, that's just 3 digits, 1, 0, 1. The other 5 digits in front that are always present are not used. Again, we have exactly 8 bits. We always have to use all the 8 bits. It's just that most of them will then stay 0. So we have 5 zeros, a 1, a 0, and a 1. That's what you can imagine. Let me write this out. We have the number 101, but we need 8 digits, so we have 5 zeros, a 1, a 0, and 1. And then when we shift to the right, what we're left with is this. And then when we shift that to the right once more, we have this. And finally went up with this. Every time we shift over the number, we're losing 1 digit and the rest is filled with zeros. So after only 3 bit shifts, we're already hitting this state, which is guaranteed after 8-bit shifts, but we already reached it faster. And what is this state? Well, this would be number 5. This is a 2. This is a 1. And this is 0 in decimal. So what we can look for is the value of the accumulator after the shift being 0. If it's 0, we don't need to repeat anymore. And we can just keep track of everything by writing this back to A. So the next time we repeat, it's the already shifted value. And right after loading it, we can make a jump of 0 to end. And like that. So we load A. If it's 0, we just stop. It's essentially the same shortcut we had for the other program. As part of the normal check, we just look if it's 0, and if it is, we can end the program. Nothing to be done. And if this is the very first time we run, that means we multiplied 0 by something and we can end anyway. If it's not 0, that means there's at least 1 bit set. So we shift to the right, and we save that back into the memory, and then we compare if that 1 bit we moved out was a 1, and if so, we perform an addition. Now the addition is the next crucial part. We could just add B, but that would not give us the correct multiplication. If we do it by hand, we don't add the number directly. We always have to shift the number over. When we check the very first digit and it is a 1, we add B as is, sure. But if it's now the second time we run this code, that means we look at the second digit of the original number. If that is a 1 and we want to add something, we want to add B, but shift it over to the left. And filled with a 0 in the gap. Just the normal, manual, by hand multiplication. And when it's the third time we run this, we want to shift over B to the left twice, and then add it. and the third time we want to shift it over by 3 times and then add it. So how can we shift b over exactly the number of times we've run the loop already? We could use a counter again. We can use a counter that increases with every iteration of the loop, and then depending on the number of the counter, we repeat a bit shift in b and then add product to that. That's doable. I mean, it's exactly the program we used to before, right? Our old program multiplied by repeated addition. We can use the same code just with a bit shift instead of an add to make repeated bit shifts. There's an easier way though. One that's way less complicated. We want to shift b over exactly once for every digit we dropped, for every repetition of the entire code block here. Why not shift b over every time we run this entire code? Every time we repeat this and shift over a to the right, we also shift over b to the left, regardless of if we use it or not. That way we have it always shifted over exactly the number of times we need to. So if I shift over b, let's say I write b to the accumulator, make bit shift left, and then write that back to the memory. It means we can also remove this no operation, because now we have something to point to. It means we start our program, we stop if a is 0, otherwise we make a bit shift right to check the value, store that of course. And if that value was 1, the flag was set, and we're gonna run this addition. We're just gonna take the previous value of product, 0 in the first iteration, adding b to it, at least the current value of b, striving that. And then, regardless of if we executed the addition or not, we're gonna take b directly, the actual value of b, shift it to the left by 1 and store that. And then we'll repeat the entire thing. Assuming a isn't 0 yet, we're gonna take the last digit, check if it's 1. If yes, we're gonna add the new value of b, the one that's shifted over by exactly 1. Shift it over by 1 to the left more, so now it's shifted over by 2 positions, and we repeat. So next time when we add the value of b shifted twice. And even if we don't add anything in between, if there's just a bunch of zeros, we still shift over b. So every time we check one digit from a, we know b, the value we add, is going to be shifted over the exact amount of times, just in the opposite direction. If that doesn't make sense to you right now, maybe you should just write down the program flow. Maybe it helps if you see it happening. That might be a bit more difficult because you don't see the binary values in here. That's a slight disappointment, I have to say. Should have made that better. That thought didn't occur to me until later, as you'll see. In any case, this program, in theory, will calculate the product of a and b using a different method than repeated additions. Should we try it? Actually, let's just jump into the end and see what's happening when it's ending. Oh, it is. 5 times 10 is 50. That is indeed correct. We can include the same shortcut we had earlier. Didn't do that yet. We write b to the accumulator and jump of 0. And like that. So now we have the same conditions as before. We have a shortcut for if either of them is 0. We just jump straight to the end. And if not, we make the full calculation for the product and output that. So let's repeat the same values we had earlier. So we had 10 times 5. That was our first example. In the old code, that was 85. 85 instructions. Now it's 49. All right, let's take 9. In the old code, that was 77 instruction. Now it's 49. Let's try 4. That used to be 37. Here it's also 37. And lastly, go for just 1. It's 17. In the old code, that was just 13. So, let's see if we can display that down here. Can I? Yeah, that didn't work out the way it's supposed to. Let's do it like that. Ah, that's slightly better. Like that. The formatting is... should have used a different font. Anyway, this is roughly the end result. So this is our old code, 85 to 49 in the new code, 9 times 5, 77 to 49, 4 times 5, 37 to 37, equal. And if it's something like 1 times 5, the old code was technically faster. So the new code can be quite a bit faster. Let's go for 100. Let's not even talk about if this was faster in the old code. It definitely wasn't faster. With this new code, 100 times 5 is not 100 additions of 5 to itself. We only get to 81. Again, the old code took already 85 instructions for just 10 times 5. The new code is 81 for just in 100, just 81 instructions for 100 times 5. There. So it's definitely the better algorithm overall for most values. But if you look at this down here, equal at just 4 times 5, and for a 1 in front, the old code was faster. So the algorithm is generally better, but not always. It's hard to come across situations where you find the perfect algorithm that's always beating the other, unless the other one was built very badly. But we've optimized the repeated addition quite well. So, of course, this new code, which is quite a bit more complex, that uses quite a bit more code, will be a bit slower if there's barely anything to do. The old code just made one addition and that's it. This new code has to make all these bit shifts and check the result and make another shift and add and whatnot. There's all these extra jumps. You have to have some higher numbers for the overhead to really be worth it. Actually, something else about this code that might be interesting. Let's check some numbers. So let's take 15 times 5. That's 53. For 15, we have 53. "53 instructions when we use 15 times 5. Now let's use 12. 12 times 5. gets us to 49. Let's use 11. And 11 gets us back to 51. And as we tested earlier, 10 times 5 gets us back down to 49. So not only is this new algorithm not always better than the old one, it isn't even consistent in of itself. So the size of these numbers is not what determines the amount of time it takes to calculate the result anymore. And I'm making it somewhat of your homework now to figure out why these numbers are the way they are. Why is 11, a number that's definitely smaller than 12, taking more time than 12? And why is 10 and 12 the same amount of time, even though they are quite a bit different? It's also the amount of difference. 15 to 12, that's 3. And it takes 4 iterations more, or 4 instructions more. But 2 instructions already give us the difference to 11, which is just 1 less. So it's not all that regular, is it? Simple explanation. I'm sure you've already thought about it, but if not, try to figure it out. What exactly determines the amount of time it takes to run this algorithm? Enough of that for now. Even if you perfectly understand the algorithm, the idea behind it, the code itself you look at right now is, despite using assembly, a bit hard to read. Like, if you just give me this code without context, it would take me quite some time to figure out what's going on here. I mean, at least I see some distinct blocks, so that's assuming that was intentional, that will help me some. I mean, over here, that's easy to see. Some memory addresses are at there. This 100 might be a bit weird, so I should probably make a comment just to make sure no one misunderstands what this 100 is. This is an output marked as N, so yeah, that's probably sensible. But if I look through the rest of the code, yeah, that makes sense. Jump if B is 0 to the end. Makes sense. And then you write to A and jump to the end if it's 0. Then we have a bit shift and read A. And then we have this combination of 2 jumps, which, what does it do? Either we jump to add. Where's add? Where's add? Oh, it's down here. And otherwise we'd go to after add. Where's after add? There it is. And then you have to figure out, okay, so this is just inverting the jump a flag to maybe use this code or not, and then this code gets executed, and then we go to start, where star, it's up here, so we repeat this entire thing. You know, you have to work through it. Like first what the structure of the program is, and then think about what happens with these numbers, what is the goal. But it will take a bit of time. There are some patterns here though we can make use of. Just as we can use assembly to make the machine code more readable, we can use a similar method to make assembly more readable. Let me quickly make here a little... there. Oh. A bit easier that way to see. And let's also just put this over there. If you have a look at this code and this code, just these 2 blocks, they are actually structured very, very similar. Almost identical. They don't do the same thing, but they are structured the same way. We have one block of code here that reads the value from memory into the accumulator, changes the value in the accumulator, and writes the value back to memory. We read a value from memory into the accumulator, change it in the accumulator, write it back from the accumulator to memory. This tuple is always the same. Put it into the accumulator, change it, read it back. Put it in the accumulator, change it, read it back. And even over here, put it in the accumulator, change it, read it back. The only reason this doesn't look the same is because of this jump in the middle. And we can actually sort this out by putting it like that. It's a bit of a waste. I mean, additional instructions we would have to run. When we repeat the entire code. Like, this makes our program slower, and we need additional space because now I have this additional operation here, or instructions. But this makes the entire code very similar to this one now, and this one. They all look the same now, more or less. What if, instead of writing this out as 3 lines every time, we simplify that? Break it down into what it's actually doing. And what are we actually doing with this one here? Or this one, or this one. We change a value in memory. Let's assume that we don't care about the accumulator, because the accumulator is changed all the time for all kinds of purposes. We shouldn't really care about that changing too much. But the memory changing, that's a big deal. That's important. So the focus of each of these blocks is changing the memory. We change a specific address in memory. So this is changing the memory address of product. It's setting product to something. And what is it setting product to? Well, it's setting product to the value of product plus the value of B. Well, okay. Product to product plus B. Right? So this comment will give us an adequate explanation of this entire part of the code. Set product to product plus B. Makes sense, humanly readable. Let's drop this entire part. Let's not make this a comment, let's make this part of the code. This is now code. We can do that. Why not? Let the computer figure out what this actually means. Let the computer figure out that this means we read product, we add B, and we write back to product. It's all in here. It's still very well structured. It's very easy to figure out what this is doing. It's just not just humanly readable, it's English. It's just a sentence. I mean, awkward sentence maybe, yes, but it's just an English sentence describing what we're doing. And we know that this will translate back into these instructions. Pretty straightforward still, pretty simple. Same with this one. We're setting B to B, shift it over to the left by 1. How do we express that? Well, to indicate that we shift, let's just use an arrow key, just to indicate that it's shifting to the left or the right, and we're shifting it over by 1. Let's just use a 1 in here. So this is setting B to B, but shifted over to the left by 1. And we can use the same for this. We're setting A to A, shifted over to the right by 1. I'd say this, and this, and this is much easier to read than 3 instructions each, right? I mean, even if you don't understand programming, like, you don't really have to think about assembly even anymore, what these operations could mean. You don't have to know what these are and how they operate. You just know, okay, I have a product and I'm setting that to product plus B. Oh, I know what this is, so product plus B, and we're setting that to that. Makes sense. I might be a bit weird about this symbol, but if you explain, that's just shifting that over. Like multiplying by 10 or dividing by 10 if you're using decimal numbers. Yeah, okay, that makes sense. It's a bit like scientific notation, like multiply by 10 to the power of 1. Well, for us it's multiply by 2 to the power of 1. Simple enough. And there's actually another pattern we can see here. It's with these jumps. What do these jumps actually do? Well, let's start from the beginning. This jump jumps to the end if B is 0. So this thing is just so that we can skip this entire code if B is 0 and continue here. So this and this. One long segment of code that is completely skipped if B is 0. This code just says, hey, skip this and this if A is 0. But same principle, we just skip entire segment of code if this condition applies, if A is 0. Of course, this one is a bit special, but we'll get to that in a moment. And down here we have basically the same again. This just means skip this code if the flag is not set. The only thing that makes it different from these two is that we invert the condition. But otherwise it's still straightforward. But depending on the condition, skip the next block of code. We have a problem here now a bit with the names, the references in here, since right now I have these sets blah 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 to blah blah blah, which means I don't see the full assembly anymore. So I don't have access to all the references and names that were part of those 3 code instructions in assembly before. So let's not rely on these addresses anymore and boil it down to the essential. What is it actually doing? Well, this code just means all of this should be skipped if B is 0. Skip if B is 0. Just write it out in English. And to know how much we skip, let's add a little end of skip. So we know this is where we start skipping, and this is where we end. And because that itself is a bit hard to read, we can add a bit of space in the beginning. We now remove that and make a bit of space free here. And that as well, just so everything is in one side here. This will quite easily tell us that this is all part of what we're skipping. skip if b is 0, alright? If b is 0, we're gonna skip this entire thing that's following, and we know we just go straight down, this. All of this little indented part is what we skip. So if b is 0, we can ignore everything in here, just go straight to this line and know, okay, this is the next thing that happens when b is 0. But if b is not 0, then we're just gonna run this code. A bit easier to read. Let's do the same with this inverted one down here, because it's annoying me that it's just in the middle of these sets with that gone. This is also skipping. It's only skipping this part though. But when is it skipping? It's skipping if the flag is not set. So we want to skip unless flag. Oops. Can indent that again, so we know where it belongs to. So this is part of the skip, and this will skip the code unless... let's make this uppercase. Doesn't really matter, but maybe... looks maybe a bit better. Nah, who cares? This will be skipped unless the flag was set. And the flag can only be set by this operation, so we know if the bit that was moved out was 1, this code will be executed, otherwise it won't. Leaving only this last jump. And I mentioned earlier that it's a bit special, because in theory, what we are skipping is this entire code block here. But this code block ends in a jump that brings us right back to the start of the very thing that skips everything. So this and this belongs together. It's not just a straightforward, yeah, just ignore everything in here and we can just continue. Unlike these two cases where we skip and just ignore everything else, this one means we skip it, but usually we don't skip it and actually repeat. This entire block of code is continuously executed, repeatedly executed. And instead of calling it just a skip with a jump that goes back up, why not use this special scenario with a different name? Instead of skipping, we're just saying we repeat a certain part of code. We repeat this part of the code as long as A is not 0. So we're gonna repeat until A is 0. And down here we end the repeat. We end the repeat. And that's done. So if I look at this now, wait, we should probably should also indent that in here. Make everything a bit easier to see. Let's make it a bit compact. What's going on? Like that. Should maybe make the indentation a bit more striking. Yeah, I think that's a bit easier to see. So we skip this part of B is 0, and then we're gonna repeat this part until A is 0, which it could start as 0 and then we just ignore everything, but otherwise we just continuously run this block of code until A is 0 at some point. And every time in this iteration, we start by shifting over A by 1 to the right. Then if the flag was set, and only if the flag was set, we're gonna add B to our product and then shift B over, regardless of if the flag was set, shift B over to the left by 1. Only to repeat everything. And once everything is done, we just output stuff. This part bothers me still a bit. What are we doing here actually? I mean, this entire block of code is just defining some special memory cells, giving them name because we're gonna use these to store data. One of the biggest issues here is that if I accidentally execute my code and end up here, if I don't have the stopper in place, then, well, we're trying to execute this as code, which could be an issue. So we'll probably add something like a jump. Let's put a knob on here. Define block. Define. Yeah, whatever. Like that. So if we ever get to this point, we'll just jump past these values and are done with it. So there's no risk of us accidentally using our data as instructions, unless we specifically jump into these positions. But if we do, then we either made a mistake in the programming or it was very, very deliberate. And because I don't want to write this out every time, why not call it define A, B, product, like that. And since we wanted specific values, let's give them values 10 and 5. And product, we don't care, start at 0. Actually, since we don't run risk of executing this, we can put this at the very top of our program. So when we go into it, we start with the clear information of, okay, we have an A, which is 5, a B, 10, a B, which is a 5, and we have a product, which is going to start out at 0. Doesn't really have a definitive value now. And then we just read this stuff in plain English. And that tells us what the program is doing. It doesn't tell us how it's doing that. We don't know what the assembly looks like. I mean, I know, but you as just the programmer that just reads this, you're not too sure. Could be anything. You just know this is describing what the program is doing, and it will do that. We can load this program. I can run it. And yeah, we're already in the knob zone. Program is done. No stopper anymore, and the output was 50, which is correct. Let's go just back to 1. Load that as a program. And that's 5. So the program is running. It's properly understanding what this means. But it's a lot more readable already. Especially compared to machine code, but also compared to raw assembly, this is much easier to work with. Because we don't have to worry about the mental strain of, okay, which address do I use here, and how do I arrange these commands to not accidentally overwrite my accumulator while I use it for another operation, and how do I keep track of all these jump instructions in between. That's not my issue anymore. The computer will handle that for me. There are downsides here, though. Let me show you something. If we just look at the result of what the computer will turn this into in assembly, that's what we get. Now, the weirdest part about this is the names for the different addresses. Like if you look at this or these symbols here, those are all just names. The intention here is that these are symbols that you wouldn't use as a human in normal programming. And so you don't run risk of the generated assembly accidentally conflicting with values you defined. So it's not going to accidentally use product or A as a name anywhere in here for its own generated code. It's just to avoid conflicts. But otherwise, this is the code it generates. You don't see the individual blocks anymore, but one of the most important parts here is you can see this knob. You might recognize this from earlier, which is straightforward, just the jump instruction I used to jump past the definition of our variables. Well, this concept with a knob, in this case, we could skip it, right? Instead of putting the knob here and then going to our write accumulator, we could just take this, put it directly to the write accumulator and drop the knob. Make the code a bit shorter and faster. One instruction less to store in memory and one instruction less to operate with. And if you look here, there's another knob, and there's another knob, and there are two knobs down here. And of course, stuff like that, stuff like we had earlier. Where is it? I'm not sure if I can find it again. Where we compared the value of A and then shifted A. Oh yeah, here. These two. We write A to the accumulator and we jump if it's 0, and then we write to the accumulator again. But the accumulator wasn't changed, so in theory we could just drop this, lose another instruction, but the program would just work the same as before. And over here we could remove that knob, put that in here. Right? Stuff like that. There's a lot that the computer would do here that we wouldn't do as a human if we completely do it by hand. Because we see, oh yeah, we can optimize this. We can make this faster, streamline it a bit more, make it more efficient. But for the computer, turning this into this follows a very strict formula. It sees a certain statement, and it knows, okay, I have exact instructions for how to turn this into assembly. And this set of instructions is always looking exactly the same to make sure it will always work in every circumstance. It's not gonna factor in other parts of the code that this might be able to interlock with to make things a bit more efficient. That doesn't mean you can't get a computer to make this more efficient. It's just that by default it will start off like this, without any considerations for making the program a bit faster. What you usually have in modern compilers, or just runtimes or whatever you use, is additional systems that can either support the compiler while working on stuff, but often actually work on the end result of what the compiler provides, and then just trying to find ways to optimize this part of the code. So it can either work while you compile, which is what we would call turning this into code that the computer can understand. But you can also operate on the end result of the compilation and just work on that independently, which means you could also use that on human-generated code. That's optimization. And of course, all of this then gets turned piece by piece from normal assembly code into numbers for memory. just the same as before. But it starts off now as just plain English that we can interact with as normal human beings, civilized beings, that don't have to worry about the intricacies of what the computer is actually doing. Because not only do we are not reliant on the opcodes anymore, we don't have to worry about which opcode was addition. We don't even have to worry about addition anymore. Just we want in effect to have an addition happening and store that in product. But how that is done, I don't care. The formula by which the computer can turn this into assembly code can vary widely. I have my 3 set instructions for this: write to accumulator, add, read from accumulator. That's working for this CPU. A different computer might have very different assembly, very different behavior internally, and might do things very differently. They might not have accumulators. Not every computer has an accumulator. It doesn't always work like the one I have here. Actually, I think that's one of the more rarer systems. It's just very simple to understand. So, depending on the computer, on the hardware, this can look very, very different assembly. But it always functionally does what you set out to do, written in plain English. And it's a lot easier to understand for someone who is not as well versed in the specific assembly dialect you're looking at. This is a higher level language. This is what we are gonna work with in the future. Well, sort of. This is still a higher level language. Higher level just means we are separated from the assembly and we now talk about what we want to achieve. And some other systems, usually automated systems, will then try to interpret this and turn that into actual instructions, usually first into assembly, which in the end will result in machine code for a computer to execute. But we are now separated from that. Once we're at this step where we work with the higher level language, we don't think about the assembly anymore. We don't think about machine code anymore. We don't think about how the CPU operates anymore. That is past us now. Doesn't mean we are not able to interact with it though. If you look over here, I still have my write IO, an assembly call. I mean, I don't need the AND anymore. Can ignore that. But this is still pure assembly. And it just works flawlessly by combining it with this higher level part. Well, this higher level part. That's not always possible, but in many languages you have the option to write your higher level code that describes what you want, but at specific sections or using specific methods, you can still give very specific instructions in assembly. If you think you know better than the default systems in the compiler, then you can do that. And there might be good reasons, especially if you have a target system in mind, maybe your own, where you have some rather unique circumstances and you know you can take advantage of something that the compiler just would not have a way of knowing about. Then you can interject something, use assembly, and do the work yourself. And that way you can optimize things or make things possible that the standard language doesn't offer. That can also happen. That, for example, if the system that compiles this into assembly might not understand what the bit shift is. Which is weird to say, but maybe it doesn't. Maybe there's a special operation that you can use for bit shift that works different from the standard one. If the compiler doesn't know about that, it will still try to make the bit shift happen, but using the method it knows, not the better, more efficient method that you know your PC can do. In that case, you would not let it do it like this, and instead you would write this out by hand. Just as a side note. Now, with this higher level language, there's one more feature we can do. It's something we haven't seen in pure assembly before, and it has to do with a very simple issue. This entire code is doing exactly one multiplication. Say I want to do another multiplication. Well, guess I have to copy the entire code and let it run once more. And third multiplication, the fourth, you can't even see it anymore because it's too much. Certainly I can do that, but that's quite a lot of memory space that I need for the exact same code. Also, we might not be sure how many multiplications we actually want to do. Just as we did with the multiplication algorithm in the beginning, where we had multiple additions based on a dynamic input, we might want to do multiple multiplications based on a dynamic input, like exponentiation. In that case, we don't know how many multiplications we need to do beforehand, and we have to do that dynamically. We can do that in loop, of course, but the places where I want to do multiplication might be in various different parts of my program. Maybe even in completely different parts of my program that are not connected, that I don't want to always repeat in the same loop. How can we solve that? Well, we have a jump instruction. We could jump to the beginning of our multiplication code, and then once it's done, jump back. Sure, that would work. Only this jump back, well, it's jumping to a specific address and back. Could be here. This is where it's jumped to. If I want to make another multiplication over here, well, I can't call this back as well. I can only jump here or here, not both. That's where a special jump operation comes into play, one I showed you last time in the instruction set overview. We can use a swap. Just a reminder, swap is a single operation, there's no argument, that will take the value in the ALU and program counter, and it will swap them. So whatever value was put in the accumulator is now the new instruction. There's now the new program counter pointing to the next instruction, like a jump. But at the same time, the previous value of the program counter is now in the accumulator. And once it's in there, we can manipulate it and we can save it. So let's say we jump over here. Let's say this is just the address where we want to start. We can write the address to the accumulator, and then we call this swap. And once that happens, we'll jump back up here, and the address of the swap is now in the accumulator. So if we read from the accumulator to jump back, that means we now store the address for where to jump back in jump back. And if we beforehand add 1, or like this 1, to the address before saving it, we're gonna save the address below the swap. So if we jump back, we can jump back to this address. And then we can call that another time. And we do it down here. We write the address into the accumulator. We swap accumulator and program counter, which means we end up here. We add 1 to the address, or to the value in the accumulator, which is the address of this swap, and save that as the return address to jump back to. Now this is a bit complicated to set up in assembly, because you have to be careful with the references, and sometimes it's the value itself and sometimes the value in the memory address, and you can't set it up in assembly. It looks a bit weird though, and I'm not going to expose you to that unless you are really determined, in which case you will figure it out yourself. In the higher level language, we have a name for this concept. It's called a function. It's a pretty common thing. Functions exist in basically every language. There are languages that are only functions. Let's move this over a bit as well. And functions have a name. This one, let's just call it uppercase mul. Just in honor of the other operations we have add and sub, now we have mul. And to use this function, we can simply set, let's say, a to 3 and set b to 4, and then we call the function. Let's move that on here, and then we can write product. So we don't need to do that anymore, like that. One thing we will have to change, the first thing we do in a function is ensure that product is 0 to 0, like that. Why is it? That's better. So in the beginning, we define a, b, and product, and our function will start by ensuring that product is 0, which, as you will see in a moment, is not always the case. Otherwise, it will just use our normal system for multiplying, and then the function ends. In the normal circumstances, this function will be surrounded by a jump before with a knob in the end, so to make sure that normal code doesn't execute this. Just like the definer here surrounded the different memory addresses, we gave a name with a jump instruction. And then here, I'm just setting the values to what I need right now. Could be by hand like this, or it could be by some other code that would generate values we store in A and B. Then we call mult for multiplication, which will cause the program to continue execution in here, setting product to 0, calling our multiplication code, and once it reaches the end, it will just straight up go to the next line after the call and continue here. So we can do that once, and we can do that, well, let's make that like that. It's first 12 and then 13 times 9, like that. Call it again and write the output. Let's load the program. So you will see this start out as 0 in the IO register. Once we hit the first call and output this, it will switch to 3 times 4, which hopefully will show us 12. And because I'm not going to stop, it will then continue to call this a second time with 13 and 9, which should show us 117, I think. So let's see. There was the first output. It is indeed 12. And 117, I was right. Good. My brain still works somewhat. And that was the second multiplication. So by using this concept of functions, which is just making sure that you have a piece of code exist once in your memory while being able to use it repeatedly. By doing that, we can define our own operations in a way. Instead of calling add, I just call mul for multiplication. And now imagine our original code for the addition, for the repeated addition for multiplication, where we just repeatedly add. Now imagine instead of an add, I would do this. I call mul. In that case, the original code for the first version of our multiplication would turn into exponentiation. I'm not going to do that here because there's too little space and you wouldn't be able to see it anyway, but it's just the original code, and we make sure that A and B get the two values we want to multiply and call multiply, and then we can take the product and write that into the memory we need the result in. So it's a bit more to write out, and it's definitely a lot more code that's executed in the background, so the instruction count will definitely be a lot higher. But we can fit it inside relatively little space in our main memory. We just reuse some parts of the code multiple times, and that way create a large program. Constantly expanding what we can do. Instead of just addition, we do multiplication, and then we can create a function that does exponentiation. That's internally using this mul function to do multiplication, which is internally using addition, the basic operation. And then maybe you can also do something like square roots, which are also pretty simple actually to calculate, at least if we all stay in integer space. And then maybe we can do functions that use these numbers more like decimals. So we're not limited to integers anymore. Or maybe we handle systems to deal with them as negative numbers. Maybe we can expand to use multiple addresses together as a number instead of just one. In that case, we would have to write our own functions for things like add and sub and bit shift and whatnot. But you can do it. And you can then slowly expand the capabilities of your program and just put the new functions in the new functions, get better tools, use those better tools to get even better tools, to get even better tools. And that's how you end up with a stream like this. Enough of that. We've been talking for 2 hours, or I have been talking for 2 hours. And all of this was a bit mind-bendy. I assume this was rather dry, since you didn't learn as much new stuff and it's just exercise for the most part. There's one last surprise I have ready for you. This thing you see is a program I've written, or started writing over a year ago. Most of it was finished by then. And then a couple of months back, I started writing a second version of this. And while this one is available, you shouldn't use it because it's really optimized for my case, and the code is so ugly. It's so ugly. I've made so many weird choices and just random workarounds and just, I don't care. It just needs to work. Like that kind of code. What is available and looks actually rather nice. The code isn't too great, but the program is quite nice. I think. It is this. I call it Tipsy. It's a pure console program. The source code is available online. Let me just put the link for the downloads. It is for the current version, which is 1.0.1. In the chat. I hope I remember to put it in the description of the VOD. You can find the release there, and you can of course look at the source code itself if you want to do something. Again, it's pure console based, so no specific UI. It's written on .NET, but it's framework independent, so you don't need to have .NET installed. And the compiled version I provide in the releases are for Windows and for Linux. If you have the source code, of course, you can compile it for your own system, whatever you need. Let me quickly show how to operate it. Let me load the program first, maybe. Where is it? So, when I started Tipsy, I provided the path to a specific text file as an argument, which means if I press L, it will load that program. You see how the numbers all up here appear. Let me compare that. Wait, where is it? If you compare the numbers in here to the numbers in our original, 8500, blah blah blah, 5394, well, 850, blah blah, 5394. This is the program we're running right now in the stream, or we wrote in the stream, just in the console version. And you can step through this step by step, like I did before. This would be essentially advancing the CPU clock internally. You can see it in the bottom right here. You have the CPU clock ticking up and down. Or you can just go with the left and right arrow keys, with the up and down arrow keys, just instruction by instruction, which is what I did in the end. I can at any point just reset the program to go back to the start, or I can press L again to read the current state of the text file I associated everything with to just load new code. So you can keep the link to the file open and make changes to your source code in an editor, then just press a button and it will load the new one. Also, what I mentioned earlier about, you'll see later how I changed my mind or changed things. I'm not limited to decimal anymore. I can also look at the binary representation of everything. And if you're feeling fancy, I can look at the hexadecimal version. Let's maybe look at the binary one. Now, of course, it's hard to see when we're hitting the shift operation, but actually that might be it. Bit shift right, okay. Pay attention to the accumulator right now. We have 1, 1 in there. And we're now processing the operation. It's 1, 1 now, and the flag is not set. Now it's just a 1. We shifted over everything 1 to the right, which means we dropped the 1 and the flag is now set. We shift left. We look at the number. It's 100. And we process the operation. It shifted over 1 to the left. And because the number we dropped out was just a 0, the flag is not set. And that's how we can slowly work through our program. And of course, in between you get input and output. Now, input and output, there's something you should know. Let's load a new program in, read.io. Let's make a simple addition program that takes 2 inputs. CK and B, C, and then write.io sum. Okay, and let's reload the program. I made a mistake. Oh yeah. So while compilation was happening, there was an error. So I have forgot to add the names. So this is A, B, and sum. That's better. So we run, I just skip to the next instruction, but the first instruction was an input-output, so now you can see it highlighted. The way it works, if I press a number, like let's say I press 4, just the number key, you can see it's now 4. Now let me press a 2. You can see it shifts over the entire number and just adds the new value on the right. And let me press a 3. This is now happening because it can only store numbers up to 255, and 423 was a bit too much. If I just add 1s, add 2s, add 1s, you can see it always shifts them over. If the numbers get too high, it will crop them. That's just what happens. Works for the different number systems as well, so I can go 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0. Sure. It will accept other numbers as well, but that might not be what you want to. And of course, for hexadecimals, I can just add the letters as well as the numbers. It might get a bit weird sometimes if you accidentally hit a number that's not available in that system, but once you get used to it, it's actually quite simple. And of course, if you want to delete everything, just press 0 a couple of times and then the number will be 0 and you can start adding something again. Other than that, special things about this. For one, you can have the system output the individual stages of, let's call it compilation, when you provide a full code. So if you're interested in how it's breaking down that stuff, you can have a look at that. And one special thing, instead of just showing the input-output here, it can interact with files on your computer to read input and to write output. It would work by output is just, it will attach the value that was output to the end of the file. So it will constantly grow a specific file you provide by adding a new line with the next value that was output, if you want to check that later. And input works similar. If you provided a line and file for input, it will read that file line by line and try to parse every line as a number and then use that number as the input whenever it requests input. So if I go back to the start, if I were to use a file, it would read the first line now from that file and use that as the input number. And then for the second input, it would now read the second line in that file. And it would do so whenever you have read IO. And if it reaches the end of the file, it will just start the very first line again and cycle through all your inputs. Which gets interesting if you combine input and output in one file. And suddenly you have a system to expand the memory from 255 to whatever you want. It's a bit weird to store your memory like that, especially because you can't erase it anymore, but you have this write once memory that you have to cycle through. It's a bit weird like that, but it can be done. And of course you could write, in theory, a program that's nothing but a bootloader that then while running will use the input to read an actual program from the input file. So there are a lot of interesting scenarios you can play with using this little console program. I think that's basically it. If you're not sure about the specific instructions, of course, and how everything works, on the page there's a full README with all the details, and if you start Tipsy itself without any arguments, actually work? Wait. There. It will show you the same documentation as well, so the different arguments you can provide, the full instruction set, and the syntax for the high-level syntax. All of that is in there. Go and have fun. Post on the pages if you find any bugs, but I'm not sure if I will actually make any changes to the program anymore. it does its job well enough, I think. And it's not intended to be full tool, it's more for educational purposes, so I don't see a point in making this even fancier. And with that, we're closing our look at CPUs themselves. Take a good last look at this made-up CPU. We're not gonna see that again. Not until next year when I restart the series. Next time, we're starting with C#. Ooh. Well then, have a lovely Sunday. And have fun with Tipsy. And until next time.